And so now when we go, let's see what's coming next. Oh, I've got a whole nother slide. So now we can say that psi of phi, so we know that this is imaginary roots. So that means it's going to be a, some normalization constant, e to the I ml phi plus b e to the negative I ml phi. All right. And so now what we're also going to look at here, because we recognize that ml can already be plus or minus, we technically can just write this as psi equals a e I ml phi. Again, because we already know that ml can already be plus or minus. All right. And so now, let's see, when we go to normalize this thing, it's pretty straightforward, okay? So we're going to normalize it as psi star psi, right? So that's going to be n squared over, so we don't need to worry about the theta or the r. They're gone, right? So we're just going to go from 0 to 2 pi. So I'm replacing my a with my n squared, right? And now we have to remember, because that's got an I in it, my psi star is negative ml phi. So that's really important. So I have to consider that conjugate now, right? Because we're dealing with i's. So now when I go to plug these in, right, it's going to be e I ml phi, so negative, I'll do the conjugate first, times e I ml phi, d phi, and that all has to equal 1. Well, check out what's going to happen. So these two things eliminate each other, right? It just becomes 1. And so now I've got n squared from 0 to 2 pi of d phi equals 1. And so we know that then the integral from 0 to 2 pi of d phi is just 2 pi, okay? So now that's 2 pi times n squared equals 1. And so we can see finally n, the normalization constant, very simple, is just going to be 1 over square root of 2 pi, okay? So what does this mean now? Well, what this means, for one, if we look at our wave function, I'm going to write the wave function as psi of phi equals 1 over the square root of 2 pi e to the I ml phi. And so what about this ml? Can we get those quantum numbers that we talked about out of this ml in a different way? Okay? And so what we can do is we have to recognize for this closed loop motion, okay, psi of, so I'm going to write this up here. So psi of phi must equal psi of phi plus 2 pi, right? So in other words, the value of psi at phi, when it comes around and makes a full 2 pi loop, those two values have to be equal to each other, okay? So that means that now, so I've got this psi of phi, but now if I write psi of phi plus 2 pi, so that's going to be 1 over root 2 pi e to the I ml times phi plus 2 pi. And what do we get out of this thing? Well, for one, let's see here. We know that we can do some algebra on this. And I can write this as 1 over root 2 pi times e to the I ml phi times e to the 2 pi times I ml. So I just did some algebra there, right? Separating the exponents, okay? And so I think I probably didn't leave myself enough room. So then I'm going to write another proof here that we're going to use. So recall, I call this the God theorem. e to the I pi actually equals -1, which is really cool. And so you can see that we have that. I've got an e to the 2 pi I, okay? So I can rewrite that as the following. Man, oh man, I wish I left myself more room. So let's see here. Okay, I'm going to add a slide. Nope, I didn't want to do that. I'm going to add a slide at the end. Okay, so yes, so I'll just rewrite this again. Sorry, psi of phi plus 2 pi equals 1 over root of 2 pi e to the I ml phi times e to the 2 pi I ml. Yep, I got that. Okay. And we know that e to the I pi equals -1. So now I can rewrite this as the following. And so also, I'm going to note that psi of phi equals 1 over root 2 pi e to the I ml phi. Okay, great. So now when I rewrite this, check it out. I've got a 1 over root 2 pi e to the I ml phi. So this chunk right here just becomes psi of phi. Brilliant. So, but now I've got an e to the I pi, and I'm going to write that as -1, but then it's still raised to the 2 ml power. Okay. So now, if I continue along here, and I recognize that my psi of phi plus 2 pi has to equal also psi of phi. So remember that boundary condition. Psi of phi has to equal psi of phi plus 2 pi. So now instead of writing this as psi of phi plus 2 pi, I can just write this as psi of phi. And then now what I'm left with, I can cancel the psi of phi and write that because it comes 1 and 1. And so now I get 1 equals 1 times -1 raised to the 2 ml power. So what are the values that ml can take? Well, anything raised to the 0 power is 1, right? So if I take 1 negative just to prove this, okay, and I raise it to the 0 power, I get +1. So that means ML0 is possible. Okay. Well, what if this was ML was +1, let's say, okay? Then -1 raised to the 2 times 1 is 2, so -1 squared is 1, so that checks out, okay? But what if this was -1 raised to the -2 power? I'm going to do this just to prove that it works. -1 raised to the -2 power is still +1. So plus minus 1 works. What about plus or minus 2? I mean, let's try it, right? What's -1 raised to the 4th power? It's +1. Brilliant. And as we will find out, we can just keep going on and on and on with this, etc. And all of these ML values are possible, which is sweet. So in more than one way, we came up with this quantum number ML, solving the particle on a ring problem. Okay? And the last thing where I will leave off for this lecture, I'm going to go back to where we came.